Hi, everyone. I'm Debarati. It's great to be back in Lisbon. Thanks to the organizers for having me here. So I'm Associate Professor at Inter-University Center for Astronomy and Astrophysics in Pune, in India. And I'm also member of the LIGO and LIGO India Scientific Collaborations and Chair for Outreach for the upcoming LIGO India project. So this work is a result of collaboration with my colleagues from Goethe University, particularly Laura Zagunski and her students who are here at this meeting. And it was led by my PhD students, Swarnim Shirke and Suprabhu Ghosh. So thanks to Chris and Sanjay for setting the stage perfectly for my talk. So we already heard about the complexity of the interior of neutron stars. And so what I have been doing in my research group has mostly been exploring the signatures, looking for the signatures of this exotic interior in gravitational waves. So we have already heard many talks about the binary neutron star mergers from which we can detect tidal deformability, which gives us a hold on neutron star radii. And so what we have not detected yet, but hopefully we will soon, are gravitational waves from other possible sources in neutron stars. For example, if there are oscillation modes similar to what we get in heliosismology or earthquakes, to give an example. So there are many fluid modes that we have in stars, and particularly we also have pure space-time modes because neutron stars are extremely relativistic. So these would also depend on the interior composition. And from the detection of frequency and damping time scales, we want to find signatures of the interior composition of neutron stars. So in the last few years, me and my students, we have been looking for such signatures in gravitational waves from F modes, G modes, and so on. And so in this talk, I will be concentrating more on the R modes, which are very interesting because these are rotational modes generic to all rotating neutron stars. So we know that R modes can be unstable through the mechanism suggested by Chandrasekhar, Friedman, and Schutz. And so R modes, unstable R modes could be damped if there are viscosities present inside the neutron star. And interestingly, these are actually, so the shear and bulk viscosities depend on the interior composition. So shear viscosity results from scattering processes, whereas bulk viscosity depends on the different leptonic and non-leptonic weak processes that go on inside the star. So it's all a game of balance between the time scales of dissipation and gravitational instability. So this can be actually diagrammatically shown with this R mode instability curve on the temperature frequency plane. So here, at large densities, it is basically the different leptonic processes like the direct and modified Urka process, which are nothing but neutron decay and proton electron capture processes, which provide the bulk viscosity at high temperatures. And at low temperatures, it is mainly the shear viscosity from the particle collisions that damps out the viscosity. So imagine there's a newly born hot neutron star that's cooling down. It hits the boundary of the instability window. It loses energy in the form of gravitational waves. It spins down and hits the other border of the instability window, where this is damped out by shear viscosity. So let me also warn you that this is the minimal scenario because, as Sanjay already explained, there are many different exotic components inside the neutron star, all of which can have their own leptonic and non-leptonic processes, which can produce bulk viscosity and modify this kind of simplistic scenario for the instability window. So now the interesting question here for this audience is that can dark matter modify the R mode instability window? So as we already heard many talks about how dark matter can appear in the neutron star as a dark matter core or as a halo, we expect that as it modifies the mass, radius, tidal deformability, all these observable properties, it should also modify the R modes. And therefore, if we detect R modes, can we actually constrain dark matter particle mass or couplings? So that is the question we are addressing in this talk. So we already also heard about the neutron decay anomaly in the previous talks. So if we believe that this is not a caveat from the experiments, I mean, you have already heard there are many different dark matter models, and also there are equally large number of neutron star models. So for this particular study, we chose this neutron decay anomaly because it's interesting. It's actually easy to compute the bulk viscosity from this model. So I will come to that in a couple of slides. So we considered a dark matter model which is motivated by the neutron decay anomaly with dark matter self-interaction. So this is what the equation of state for the fermionic dark matter looks like. And here G is the self-interaction of dark matter. For the neutron star hadronic model, we used a phenomenological relativistic mean field model, which is explained by the exchange. So the nucleons, they interact via the exchange of different types of mesons, and the couplings of the mesons with the nucleons are fitted to properties of, so saturation properties of nuclear matter. So in this work, we use two different models, one which can explain most of the observational data from neutron stars, and the other one is actually from a recent publication where we imposed constraints coming from chiral effective field theory and nuclear experimental data at low densities. Intermediate densities, we had heavy ion collisions, and at large densities, multi-messenger astrophysical data. So from this Bayesian study, we took the stiffest equation of state, and the reason is that we wanted to estimate the minimum the self-interaction of dark matter that can explain the current state-of-the-art observational data. So here you can see the black line is the pure hadronic case, and the blue line is actually the one with dark matter but without self-interaction. So if you add self-interaction, so with increasing self-interaction parameter, you see that the equation of state gets stiffer until at one point it coincides with the hadronic one. So this can also be understood from the particle fractions. And actually, so if I play this again, so the dark matter fraction goes down as the self-interaction coupling increases, and therefore, at one point it coincides with the pure hadronic case. So we can, solving the TOV equations, we can obtain the mass radius curves for these corresponding equations of state, and we can put a bound on the minimum self-interaction that corresponds to the stiffest hadronic equation of state. So yeah, this number is slightly bigger if we consider masses which are above 2 solar masses. So now we want to calculate the shear viscosity and try to see what this bound on the self-interaction means in that case. So we know that from kinetic theory that shear viscosity is related to the dark matter self-interaction cross-section, which we also heard in the previous talks that this can be estimated from different astrophysical constraints. So in our case, we also imposed the bound we got from our model, and we find that the bound on the shear viscosity is actually, or on the cross-section is actually less constraining than what we get from astrophysical constraints. Nevertheless, so we calculated the shear viscosity, and as you see here, shear viscosity scales as temperature to the half. So this becomes more important at larger temperatures, whereas the shear viscosity coming from the hadronic equation of state from neutron-neutron and electron-electron collisions, these go as temperature to the -2. So these actually are more dominant in the low temperature case. But interestingly, the temperature at which dark matter takes over is also where hadronic bulk viscosity is more dominant. So now let's calculate the bulk viscosity using the neutron decay anomaly model that we are considering, and imposing the general chemical equilibrium and charge conservation conditions for a dark matter admixed neutron star. So one can calculate the bulk viscosity coefficient from the equation of state, and what is unknown here is the time scale. So we have a condition on the time scale that from the neutron decay anomaly that this time scale for this reaction should be 100 times the neutron decay time scale. So there are two possibilities here. So one is that the decay time scale of dark matter follows the temperature dependence of the modified Urca process and is 100 times smaller. Or the other possibility is that we assume the standard model neutron decay time scale, and this remains a constant, so 100 times larger. So we explored these two scenarios, and here we plot in this orange line, yellow line, the dark matter bulk viscosity at different temperatures. So this is increasing temperature. And in all the scenarios, we find that it was several orders of magnitude smaller than the hadronic bulk viscosity. So this is for the temperature-dependent time scale. And for the constant time scale, we found that actually there's an intermediate temperature regime where bulk viscosity from dark matter dominates over the shear viscosity and bulk viscosity from the hadronic component. So now if we translate this to the R mode instability window and probe the two parameters, so the two parameters are the self-interaction cross-section G and the time scale. So first we keep the time scale constant and vary the self-interaction. And we find that actually the self-interaction has minimal effect on the R mode instability window. For the different values that you can see here, these are almost coinciding except for the low temperature part. Interestingly, so we also probed the scenario for the two different time scales. Thank you. So for this, the case where the temperature, it is temperature dependent. So actually the dark matter bulk viscosity is always orders of magnitude lower than the modified Urca bulk viscosity. So that would correspond to this yellow line, which coincides with the case without dark matter. So this does not give us any more information. So the other possibility where we have constant time scale, so we see here that when we vary the time scale, this actually has a very dominant and dramatic effect on the instability window. So we now checked whether this is actually compatible with the data we have from the pulsar catalog and from X-ray data. So we superimposed these data points, and as you can see that in the minimal scenario where we have only cooling from neutron, protons, electrons, so these points, the observational pulsar, these points lie within the instability window, which means that they are not compatible with the scenario that we are considering. So, so I come to the summary. So there are many different dark matter models and hadronic models. So we considered here two models. So the hadronic model was the relativistic mean field model that is compatible with the state-of-the-art constraints from different multi-messenger physics, and dark matter model which is motivated by the neutron decay anomaly. And within this combination, we investigated for the first time how R modes can be a probe of dark matter in neutron stars. So what we found was the shear viscosity was several orders of magnitude smaller than the neutron-neutron and electron-electron shear viscosity at low temperatures. And the dark matter bulk viscosity that was resulting from this deviation from chemical equilibrium, this was also orders lower than modified Urca bulk viscosity in hadronic matter if we consider that it follows the same temperature dependence as modified Urca. In the other case, we saw that if it is temperature independent, then it does have an effect on the R mode instability window. However, this was not compatible with observational pulsar and X-ray X-ray data for neutron stars. So of course, this is just the first attempt, and of course there are many possibilities to probe with other dark matter models and hadronic models, but it would always be interesting to look for dark matter signatures in gravitational waves from these different oscillation modes in neutron stars. So finally, I thank the organizers for having me here, and also to you all for being here after the conference dinner. Thank you.
Thank you very much for the very interesting talk. We have some time.
Thanks for the nice talk. Is it possible to open the window for like direct Urca by playing around with the parameters? Because if you open direct Urca, I mean, the star will cool very fast, and maybe you can put constraints or something.
Yes, so normally we know that there is a certain proton fraction beyond which the direct Urca channel opens. Yeah. And this also changes in certain conditions, like under magnetic field or different exotic components. In this scenario, we did consider the minimal bulk viscosity coming from modified Urca, but this is something to look at as well. Yeah.
Thank you for a very nice talk. Can you comment a little bit what can excite these no-radial modes in terms of like how these modes can be excited, at least?
The R modes?
The R modes, or the R modes and the other ones in terms.
Okay, sure, yeah. So these modes you mean, right? Yes. So the first mode, so these are basically the fluid modes. Okay. So the fundamental F modes and P modes are basically restored by pressure. So all of these are like when they are disturbed from chemical equilibrium. Okay. Rotation R modes are restored by Coriolis force. So it is similar to...
But these modes are excited when in this kind of phase, they are merged? Because in normal stars, you can have excitation just by other mechanisms. Like
I see, okay.
Change. That's what I'm trying to see.
This is actually, I should have mentioned this. So these can be excited in isolated neutron stars as well as in mergers. So there has been studies which relate F modes with tidal deformability. So these can be excited also in the post-merger scenario, and the conditions will be different, so they change the bulk viscosity. Yeah. So it's an interesting
if you make an analogy with the sun and the other stars, similar gravitational knowledge, what we do, the mechanism to excite these modes is convection. And by wondering in neutron stars, if this kind of no convection, is something similar could be a permanent source of excitation of this kind of modes.
Yes, so these are actually the first modes. These are seen in heliosismology, astroseismology. Only this one is a pure space-time mode, somewhat analogous to the quasi-normal mode of black hole. Yeah.
We have time for the last short question. Please, Danielle.
Thank you very much for the very nice talk. May I ask you to go to the slide with the change of the R mode instability window, one of the last ones?
The schematic?
No, the actual calculations. One of the
this one?
Yes, this one. Mm-hmm. So I'm not so familiar with this dark matter model, so I wanted to ask you. So you made from you change, for example, in the left plot from the solid line to the, for example, to the blue one. When you change some parameters, and like the good thing is that more and more stars go out of your instability window. But how, from a theory point of view, can we actually say that these values of the parameters are relevant or not? Or this is the other way around? We will use this R mode instability window to know how much we should push the parameter so that all pulsars, neutron stars are away from it.
You mean if we choose a particular value of the damping time scale, whether these can be compatible?
Yeah, so is there any way actually to guess what is this what is the value of this tau parameter? What are these values of tau parameter that are relevant from a theoretical point of view or from somewhere
Yes.
else, or we want from here to put constraints on the
No,
parameter?
I should have also mentioned that here so for both of these, we just varied, keeping the self-interaction constant, we varied the time scale and to see what effect it has. But again, if you see the only allowed value that comes from this fact that the time scale should be 100 times more than the standard model neutron decay time scale, that means that it cannot be actually larger than a certain value. So this pulsar and X-ray data would anyway not be compatible with that value of time scale.
Okay, thank you.
Let's thank Debarati once again. Thank you. And we make a break for coffee.